So here we go for example 10, and here we're going to be looking at the motion of a projectile under gravity, and this time, instead of having any numbers in the equations, we're going to generate general equations. Now, although we're going to do that here, the important thing with this work is that you learn the routines, the approaches. I do not want you to learn the equations. In an exam, the thing that tends to happen is that they would say, show that this equation, so you'd have to do this work and then use it, rather than just using the equation having learnt them. That would not really be acceptable in an exam context. So it's the methods that are important, not particularly the answers in this instance. Okay, so here we go. A particle is projected from a point up, from a point on a horizontal plane. So we know that it's a horizontal plane. A horizontal plane, initial velocity u to an angle alpha above the horizontal and moves freely under gravity until it hits the plane at the point B, and given that the acceleration due to gravity is g, find expressions for A, the time of flight, and B, the range r on the horizontal plane. Okay, so if we scan back through the sort of yellow highlighted bits again, we can clearly see that this is going to be a constant acceleration context. So A, constant acceleration. And we've seen it many times before. The time of flight is twice the time to the highest point. So we're going to work vertically. We know that the time of flight is equal to the time to the highest point is half the time of flight. So we're going to have t over 2, because t is being defined as the time of flight, and we are only doing the time to the highest point, which is half the time of flight. A is equal to g, u. We want the vertical component, so we can put a suffix on there, y, to the highest point. So we get a vertical component, which is u opposite the angle sine alpha. And while we're doing the components, we can do the horizontal component, u adjacent to the angle cos alpha. So we know vertical component is what we're doing. We're working vertically, u sine alpha, and we want the speed at the top, v, is equal to 0. Yeah, the vertical component of the speed is 0. Now, I hope while you've been watching this, you've been thinking, come on, sir, get it right. There's something wrong there, isn't there? What's the mistake? The g has got to be negative. Okay, now, come on, Connor, you spotted that equation now, I'm sure. V is equal to u plus at. Substitute in, so we've done the state phase, we can now substitute in 0 equals u sine alpha plus negative g and the time of flight over 2, because we're just doing the time to the highest point. Add it across, gt over 2 equals u sine alpha, so t equals 2u sine alpha over g. So that is the time of flight, capital T. So now we can think about the range. Well, again, we've done this lots of times. We know that horizontally, there's no acceleration horizontally, but we still use our constant acceleration formula. So it's going to be constant acceleration horizontally, and we get A equals 0. We know our initial speed, come back to our diagram, is u cos alpha horizontally. We know that the time of flight, capital T, is 2u sine alpha over g, and our distance is this time called capital R, the range as defined in the question. So we look at our equation, and we know that it's going to be S equals ut, and we don't need to bother about the plus a half at squared because there's no acceleration. So we can now substitute in R equals u, which is u cos alpha, T, which is 2u sine alpha over g. Expand it, and we get 2u squared sine alpha cos alpha over g for the range. Okay, now we can put in a little bonus question here, which is really useful and quite interesting in some ways. And that is, what is the best angle, what angle should we project it at to get the maximum range? So to find max range, what angle should we project at? So we've got R equals 2u squared sine alpha cos alpha over g. And if we want the max range, well, there are only two variables in here. So what are the variables that we've got? We've got a variable of u. Well, obviously the bigger u is, the farther it's going to go. And we can also vary the angle. And depending on the angle we throw it, if we throw it straight up, so if alpha was 90, sine alpha would be 1, but cos alpha would be 0. And if cos alpha is 0, the range is 0. If we threw it horizontally, so alpha was 0, sine alpha is 0. So again, the range would be 0. So somewhere in between the two, there's going to be a better angle. Intuitively, you're probably guessing something. Now let's see if we can see if you're right, really. Now for that, we need an extra little bit of knowledge, which we will prove to you later on. But sine of 2 alpha is identical to 2 sine alpha cos alpha. A little reminder on what an identity sign, can anybody remember? It's true for all values. And I've just mixed up my notation there a little bit. Those should be A's. Yeah, so it should say, oops, get the right colour pen, so 2 sine A cos A. Sorry about that. Okay, so what do we get then? R equals, and we can replace the 2 sine alpha cos alpha then with sine 2a sine 2 alpha, because our angles in this case are alpha, over g, and I still need the u squared in the front. Okay, now, again, if we want the max range, we need sine 2 alpha then to be as big as possible. Yeah, so this needs to be as large as possible. So, hang on, it's that bit, sine 2 alpha needs to be as large as possible. So, what's the maximum value for sine 2 alpha? Well, max value of sine 2 alpha equals 1, which we can solve. 2 alpha equals arc sine of 1. Quickly sketch the curve, and we can see that that is 180, so it is 1 at 90 degrees. So 2 alpha is equal to 90 degrees, so alpha equals 45 degrees if we want to get the maximum range. So R max then is equal to u squared over g. So a little bit of extra information there, but I think that's quite important for you to see and understand. I hope that helps.